All right. So today we want to talk about cross products. And the previous assignment should have got you up to speed a little bit on what cross products are. I do think we should do a couple of examples. Specifically one, I want to go over a general determinant and what that is. Maybe we'll talk about what that means. So let's just do an example real quick, especially if your high school or wherever you did algebra, and you're in Calc 3, so pre-Calc, Calc 1, Calc 2 don't do matrices at all. So you would have had to learn this in high school or earlier if you ever had any sort of matrix algebra or matrix examples in high school. Maybe you learned determinants, but I know a lot of schools don't. So what are determinants? You have to understand what a matrix is. So a matrix is, let's say one here. It's going to give us a lot of different information. It's going to give us, in some sense, a higher dimensional analog of what a vector is. So at the moment, we have a loose understanding of what vectors are, namely that a vector it's a one-dimensional object. It's an object with a magnitude and a direction. So that direction gives us sort of a one-dimensional line, which we'll see once we start to parameterize lines and learn how we construct lines in higher dimensions. We'll see how our directional vector really plays a key role there. And we draw vectors as arrows. So geometrically, what is a matrix? A matrix represents, in some sense, a higher dimensional object, whereas our vectors, we can draw in space with our little dots and our little arrows. Essentially, we are attaching a one-dimensional object at any given point. If we wanted to extend this, in some sense, what a matrix is, it's kind of like attaching some sort of parallelogram at a given point. And in higher geometries, they play a very important role. And so what a determinant is going to give us is the determinant is going to give us the area of that. So whereas the norm gives us the length of the vectors, the determinant of a matrix is going to give us the area of the parallelepiped spanned by these two vectors. So you can kind of think of this as just a pair of vectors. If I want to attach, I guess other ways we can interpret it, I drew it with the dots at the center. Other interpretations are where you might have a pair of vectors at a given point, and that pair of vectors forms a parallelepiped. So we might have two vectors, 2, -1, and -3, 1 at a given point. And then the determinant is going to give us the area of this parallelepiped. So that's a little bit of geometric information. The primary information you guys need to know, especially with just determinants, is how to compute them. And then we'll see how they're used in cross products. So the determinant is going to give us, let's see. So what we have to do with a 2 by 2 determinant is multiply the diagonals. We're going to take the difference of the multiplication of the diagonals. So we're going to take 2 times 1. So our main diagonal, we're going to do 2 times 1. And then we're going to subtract off the anti-diagonal. So it's going to be minus -3 times -1. So we'll have 2. We'll have 3 minuses, so it'll be -3, and that'll give us a -1. And then higher order determinants. So you can imagine we can extend this process. So instead of just attaching a vector at a given point, now I can attach sort of these planes spanned by potentially 2 vectors. We can go up an even higher dimension and attach a 3-dimensional object, and we can still represent that actually as a 3-dimensional matrix. right? 3 by 3 matrix. In this class, we often represent our vectors as row vectors. So our I, J, and K horizontally. In linear algebra and in higher math, you'll represent your vectors as column vectors. So there's 2, -1, and a higher dimension. Let's do 1. Let's say 1, 0, -1, 2, 3, and 0. I'm going to put a few zeros in here just to ease our computation. Let's do -1 and -4 in those positions. So suppose we have now a 3 by 3 matrix, and what you can think of this as represented by 3 vectors, where our vectors now are given in columns. And again, when we take the determinant now, it's going to give us the volume of the parallelepiped determined by those 3 vectors. So how do we compute a determinant? There's actually a lot of different ways. Typically what you want to do is called, actually I guess I forget the proper name. Usually it's row expansion or column expansion. Whereas we're going to pick a row or column and then expand into subdeterminants. So the example she gives in class is we want to expand upon this first row. So we're going to start with our first position. And what we're going to do is start with this 1, and then in that row and column of the 1, we're kind of going to eliminate both that row and column. So our determinant of this guy, we're going to start with our 1, and then our subdeterminant, so the matrix that remains when we remove this row and column, is going to be 3, 0, -1, -4. And we're going to want to take the determinant of that submatrix now. The other thing to remember is when you're expanding about a row or column, the signs are going to alternate. So first row, we had a +1 there. The next one's just a 0. But if this wasn't a 0 here, it's going to come equipped with a -1. So the next subdeterminant, since we're spanning about the first row, the second entry is a 0. We can eliminate that row and column, and what's going to remain is the matrix of 2, 0, 0, -4. And then our last one, this entry was a -1. And then when we eliminate that row and column, what is going to remain are 2, 3, 0, -1. So I probably should have done each of those in color so you could kind of see which row and column they correspond to. But then you're just going to expand all those. So expanding a general 3 by 3 determinant, a little bit lengthy in the computation. So now our determinants of these 2 by 2 matrices, this one will have 3 times -4 minus 0 times -1. This expression in the middle is going to be 0, so I'm not going to bother computing it. But our last expression will have a -1 times 2 times -1 minus 3 times 0. So computing all of that out, what do we get? We'll have a 1. I don't even need to write the 1 because multiplying by that doesn't change. So -12, 0, 0, and then plus -1. That's a 0 times -2. And so it looks like we're going to get -12 plus 2. And so -10. That is generally how you would compute a determinant of a 3 by 3 matrix. You can now extend this into 4 by 4, 5 by 5 matrices, where if I have a 4 by 4, you just pick the first entry, eliminate that row and column, and then whatever subdeterminant or submatrix remains, you want to multiply that 1 or the first entry times the determinant of that sub one. And then so a 4 by 4, you'd have the determinants or the first entry times the determinant of a 3 by 3. Then you'd have to expand that 3 by 3 And the computations of our determinants get quite lengthy as the size increases. Okay, so that's determinants. I actually realized there was one small note I wanted to talk about based off of the last lecture. Let me just give you guys a tip real quick. I wrote it here on my outline. So just an aside before we get into our main topic. This might help you on homeworks. Might help you on exams. Computational tip, namely that normalizing a vector is the same as normalizing any scalar multiple of that vector. Right, so a vector has a direction. So if we scale that vector by any value, it's still going to point in the same direction. Then we can normalize that vector. It's kind of like I might have a vector that's maybe yay length that's maybe less than 1. If it's a fractional vector, the length is a fraction. Normalizing it, we would actually extend it to a unit vector. So maybe we want to find a common denominator, extend it to a longer vector, and then shrink that one. So for example, it's going to work very well with like fractions. Let's say you have a vector that's like -1/2, 1/5, and let's say -3/5 or something. So if we want to normalize this vector, you have to do that one squared plus that one squared plus that one squared, then take a square root. You got a lot of terms squared and a lot of fractions. So it's going to be a little messier to do all of that individually. What you can do is multiply this. Let's call this A. Well, if we multiply the entire vector A by, say, 10, what's that going to give us? That's going to be -5, 2, and then -6. And let's just call this a new name. Say vector B. Well, now normalizing this might be a little easier. Of course, the numbers are a bit big, but they're at least whole numbers. So norm of B is going to be square root of 25 plus 4 plus 36. So root 65. A bit quicker to get to, and that way, if we wanted the unit vector, that's A over the norm of A, it's going to be the same as B over the norm of B, since both of those are pointing in the same direction. So it's just going to be 1 over root 65 times -5 to -6. And if you wanted to be a little fancier, I guess you could then put each of these terms over root 65. So a little quicker way. And eventually what we're going to see is we're actually going to have functions within these. And so if you have to normalize a vector where functions are involved and things are changing with time, sometimes it can help you to use this trick. Okay, let me just go ahead and start on a new page. And let's talk about cross products. I don't know why I put a hyphen there. You don't need a hyphen. Cross product. So through the preview assignment, you should have covered the basic computation. So if you have A cross B, where A is going to have coordinates and B is going to have coordinates using the same letters, B1, B2, B3. And I guess one thing I should mention is that the cross product is specific to R3. So 3-dimensional space. You can use it in 2 space. You would just, the idea would be we would embed R2 in the R3. So if you have an XY coordinates and you want to take a cross product, you immediately know that the vector is going to actually point in the Z direction. So we'll mention why here in a second. But most of that you should have gathered from the preview assignment. So our cross product, how do we do a cross product? You write A and B on rows 2 and 3, and the order is important. In this case, we're using our rows as row vectors, and then we keep track of our generic unit vectors in I, J, and K positions in row 1. And so you want to compute the determinant of this. So we're going to get A2, B3 minus A3, B2 in our I direction. It's going to alternate. Remember, our determinants are alternating signs. So when we have our J coordinate, it's going to be the determinant. When we remove the top row, middle column, we will have A1, B3 minus A3, B1 in our J with our extra minus sign. And then our last coordinate plus A1, B2 minus B1, A2. Yeah, A2, B1. In our K hat direction. You should have gathered that it follows the right-hand rule, so that if I have a vector A cross a vector B, then the resultant vector, A cross B, is going to be orthogonal to both of them, following the right-hand rule. So again, we're using our index finger. Let's see if I can get this on the video. Our index finger is pointing on A.
So, but apparently not.
I'm sorry, what'd you say?
Oh, we just lost you for a sec. You're back.
What did you guys not hear?
Past 8 seconds. I don't know.
Past
Past drawing vector A.
Past drawing vector A. So I'm just describing the geometric. So this is our algebra here of how to compute the cross products. And then here's our geometry. So we've got vector A and vector B. So it follows the right-hand rule. So you want your right hand, you want your index finger pointing on A, the second finger pointing on B, and then your thumb is going to point towards the cross product, A cross B. So A cross B is always orthogonal to both A and B. So A and B is going to span a plane. The cross product gives us an orthogonal vector to both of those, and to that plane. Likewise, the magnitude of A cross B is magnitude of A, magnitude of B, sine theta. So one thing we can interpret of what is the cross product, well, I kind of started with a little bit of background on what determinants are. Cross products are actually related to determinants, and determinants actually come out of what are called wedge products. So the cross product is it's kind of a baby example of really an algebraic structure called a wedge product, where determinants naturally arise for the coefficients of computing this wedge product. But the idea really is that when I have two vectors attached at a given point can form a little parallelogram. And just as we wanted to extend from points to vectors, we're going from points or values in R1. Scalars just have a value and a size. They kind of have a direction, either positive or negative, but it's really the size that matters. And then our positive and negative gives us a notion of ordering and direction. Well, we extend to a higher dimensional algebraic structure, to this one-dimensional structure of vectors, which have a direction now. Now a vector in 3 space, we can specify what direction they're pointing. Well, if we move up to this now higher dimensional object, now 2-dimensional objects with these planes, we want this notion of a direction still. And so really, what is a direction of a plane? What do we mean by that? Really, what we want to think of is the orientation of the plane. And so the orientation of the plane is given by this right-hand rule of A cross B. The other way you can think about it is this curl mechanism. So if you have your hand pointing in the direction of A and then curl your fingers towards B, your thumb again is going to point in the direction of A cross B. So we can kind of think of this parallelogram that's formed by A and B as having this orientation of going from A to B. And so this swirling orientation, which gives us a direction of this plane. So when we take the magnitude of the cross product, just in terms of the pure calculation, if you look at what we have here, we have the magnitude of A times the magnitude of B times the sine of theta. Well, if you look at the picture we've drawn, if we have some angle between them of theta, well, kind of like how we were drawing with dot products gives us that magnitude of B cosine theta, projecting our value onto A. At least with cross products in magnitude, it's going to give us the length of this term here, which is going to be magnitude of B sine theta. Can you guys see that? This green doesn't show up very well. Let me pick out darker green, see if I got one. And so what is the length of this, length of A, times this term here is going to be orthogonal to A. So this expression gives us the area of the parallelogram. So in magnitude, a cross product gives us the area of the parallelogram formed by A and B. Conversely, well, what is just the general cross product then? It essentially encodes that same information, but also gives us this notion of the orientation. A cross B gives us a new vector that points in the direction of the orientation. So if I were to do A cross B, it points in the direction of the orientation of that parallelogram, and also encodes the magnitude, the size of that parallelogram, or the area of that parallelogram. So when we take the magnitude of this vector, we get just the area back. When we're keeping track of that vector, not only do I have that size, the area of the parallelogram, but we also are encoding that orientation as well. So let's go ahead and get started on one of the examples from the notes. Just as a pure computation, let's go ahead and compute one real quick. When we have A is equal to 421 and B is equal to 3I minus J. I guess I should say, in terms of that orientation, what would happen if I did B cross A? So if we go that opposite direction now, if I curl my fingers B to A, we'll have a downward orientation, which is why we actually want to keep track of, like, if I just have that plane or spanned by A and B, we kind of want to know that orientation. Does it want to have an upward orientation or a downward orientation, an inward or outward? We'll be using those terms later this semester too, especially once we start to describe surfaces. We want this notion of orientation because we'll be doing things like finding flux through planes and through surfaces. Anyway, let's get back to our computation. We've got our two vectors here, and we want to compute A cross B. And so we set up our ij and k in the first row. And then we plug in our coordinates, our coefficients for A and B. And we want to do A in the middle row, B in the second row. And so when we compute that, we're going to start with our I. Here, I'll do colors now. Let's do our I. So we eliminate that first row, first column. And so in our I direction, we're going to want the determinants of our submatrix. So we're going to have 2 times 0 minus 1 times minus 1. That'll be our I component. Our J components, eliminate that row, eliminate that column. What are we going to have left? And remember, we're alternating signs. So J comes equipped with a minus sign. We will have 4 times 0 times, or excuse me, minus 1 times 3 in our J direction. And then in our last one, back to a positive coefficient. And then the matrix that results is our first 2 columns. So we'll have 4 times minus 1 minus 3 times 2, 2 times 3 in our K direction. So simplifying that, let me see if I can get this on the screen here. A cross B, what do we get? 1 on the I. Let's go ahead and write it with our bracket notation. We'll have positive 3 with an extra minus sign, gives us negative 3, minus 4, minus 6. So we get minus 10 in our K. So question, or I guess exercise for you guys. How do we check orthogonality? Namely, how should I show that A cross B? Let's go ahead and call this C for shorthand. How do I check that C and A are orthogonal?
You can do the dot product with A cross B and either A or B.
Yep. Good. So check. So check both of these. I don't know if this is a homework assignment. It's always actually good to take the general definition. So if you go back to like our general, we have A cross B equaling this. Take this expression, dot product with A. See if you get 0. Take this expression, dot product with B. See if you get 0. As honor students, I would recommend you guys do that. It might actually be on the homework. Always good to do once in your mathematical career. It is a little bit of computation, but it's not too bad. It can be pretty quick. So check that A dot A cross B equals 0, and likewise B dot A cross B equals 0. It's actually a good thing to do is when you're doing with pure numbers, it's pretty quick to do as computations, and especially because cross products, little computationally heavy, and especially as you do a lot of computations in this course, it's easy to just get a minus sign wrong, or do one little algebraic computation, multiplication wrong. So as a quick check, especially while you're working out exam problems, good to check, did the cross product, did this vector I ended up with end up being orthogonal to the previous 2 vectors? And maybe we could do one real quick. So let's see what we got. So we have 1, 3 minus 10. If I take a dot product with A, we'll have 4 minus 12 gives us minus 8, and then 10. Did that screw us up? Oh no, sorry, 4 minus 6, and then plus 10 gives us, or minus 10. Oh, I'm missing a minus sign somewhere, aren't we? Should this one be positive? Did I miss an extra minus sign on J? I did. So we'll see. I made a minus sign mistake. I misread my dot as a minus sign. So this is -1 or -1 times 3 with that minus sign. So our 3 should have been positive. So good thing to check as you just see your professor making some small minus sign mistakes. So now when we do 3 times 2, that gives us 6, plus 4 gives us 10, minus 10 gives us 0. So I'll leave it to you guys. Check the other one. And let's see, anything else on this problem? Magnitude of A cross B, I'll leave to you guys. The direction of A cross B, just going to be A cross B divided by its magnitude. Check the notes for those. Pretty easy computations from here with stuff that we've already gone over. I do want to make sure we get through. How much time do we have? About 25 minutes. Let's get through the rest of the material. And if we need, we can always cycle back and fill in any other gaps we missed. So, other things to note that our standard unit vectors follow this right-hand rule. So I points in the x direction, j points in the y direction. So I cross j is going to give us k. J cross k is going to give us I. K cross I is going to give us j. So I cross j equals k. J cross k equals I. And then k cross I is going to get us to j. What's going to happen if we flip any of the vectors? So if we do, actually, we'll ask that in a second. We'll get through the properties. Let's see. Other thing we should note, what's going to happen if we do I cross I? Any ideas? If the magnitude of the cross product gives us the area of a parallelogram formed by the span of the two vectors. But if I have only one vector with itself, it doesn't form any area. It's just a line. There's no plane that can be formed. So a cross product with any two vectors that are the same is going to give us 0. So I cross I equals 0, and that actually doesn't matter. It could be like any A cross A, going to give us a 0. So properties. And again, let's go through these as true, false. First one we want to talk about is A cross B is a vector. This one, hopefully everyone can see, is true. So this is our vector product. We were talking in the last lecture that we have this new algebraic structure, this notion of a vector space. And in particular, in 2 dimensions and in 3 dimensions, we want to know what types of multiplication structures we can put on it. So our dot product is called our scalar product because it multiplies 2 vectors, but the output is a scalar. We now have this new method of multiplication called a cross product, where now when I multiply these 2 vectors, it actually gives us another vector. So it is a vector product. Property B asks A cross B equal to B cross A. So this one we want to think about our geometric meaning. What happens when I flip the two vectors in a cross product? Our dot product we know is commutative. It gives us this scaled projection, and actually geometrically this ends up being the same quantity, whether we're projecting A onto B or B onto A. Cross products, on the other hand, are not commutative. This is false. The true statement, A cross B, is the opposite, is negative B cross A. So when we think of our right-hand rule, this is what we were talking about in terms of our orientation of the parallelogram. So we have some parallelogram. If I do A cross B, orientation is upward. Whereas if we do B cross A, now the orientation of the parallelogram points downward. So it's still a vector that is perpendicular to both A and B. But if we have a plane spanned by A and B, there's actually two perpendiculars. There's one that's pointing up and one that's pointing in the opposite direction. And those are just going to be negative of each other. C, we want to take a look at our distribution law. So A cross B plus C. So our cross product is a multiplication. We want to know how it interplays with the sum of two vectors. So we get A cross B plus A cross C. True or false? So on this one, I did not throw any sort of curveballs at you. We have A cross B and A cross C, just like you would with a typical distribution law. So this one's true. And I will make a note that you do got to be careful now of the order. You do have to do A cross B and A cross C. You can't flip around B cross A or C cross A. D. We've got A cross A is the norm of A squared. True or false on this one? Well, we were just talking about it a little bit. False. Our correct statement, A cross A. Well, if I do a vector cross itself, there is no area of that parallelogram. It's just a straight line. So that's always going to be 0. And in particular, since it is a vector output, it is the 0 vector. And then on the right, so our norm of A squared, remember, that is the dot product. If we do A dot A, then we'll get norm of A squared. E, if we have two vectors that are non-zero, and their cross product is equal to 0, then they are orthogonal. True or false on this one? So just careful with the wording, careful with these concepts now. So this is all new. Practice these a lot, especially in your examples. Think about the geometric meaning, especially if you do any computations, just to keep things straight in your head, especially these first few weeks. It'll pay off in the long run for this course. This is false. What does orthogonal mean? It means they are perpendicular. Cross products give us a perpendicular vector. However, if A cross B is 0, well, what's happening with that one? What happened in the last example? A cross A gave us a 0. So what happens geometrically? How can we get a 0 vector when I take a cross product? It means they are parallel, actually. So we didn't even need the same vector cross itself. Any two vectors that are pointing along the same line, cross product is going to be 0. So careful with the wording, parallel, perpendicular, orthogonal. Let's see. Anything else? Did we talk about scalar product? Let's take a look. There was one more. There were a couple other points. Take a look on the notes on the last 2 bullets. One of them I left out. It wasn't very interesting. The other one looks like this. It asks us B dot A cross B. Is that equal to the norm of A? True or false on that one? We actually talked about this at the beginning, or at least in our example. Our A cross B we know is orthogonal to both A and B. So this one's false. B dot A cross B should be 0. Oh, sorry. Since we have a dot product, 0 scalar. Okay. Any questions? Let's get through remaining topics. We only got about 5 minutes. So some of this stuff I'll leave to you guys to look up in the notes. As mentioned before, we know that the magnitude of A cross B gives us the area of our parallelogram. Parallelogram. So half of that gives us the area of a triangle. So if you have A, B, and you want to just make a triangle out of that, half of A cross B will give you the area of that triangle. We also have the triple product. Wish I could go a little bit more in depth. I encourage you guys to work this out. Make sense of this in your mind. So if we have 3 vectors, let's say we have A, B, and then let's say we have C. These 3 vectors are now going to form a parallel piped. So it's going to be a little awkward to draw. Try to draw it quickly here. Excuse me. So not a nice cube or anything. It's like a slanted cube in all directions. Well, what's going to happen if we take A cross B? We know that A cross B is orthogonal to A and B and orthogonal to this plane and encodes that magnitude, the area of that. Well, how do we find the area or the volume, excuse me, of a parallelepiped? It's going to be the area of the base times the height, but the height needs to be perpendicular. So really what we want to do is have an object of a height, and then what we want to do is want this component of C that is orthogonal to A and B. Well, if it's orthogonal to A and B, it's actually going to be parallel to A cross B. So what we want to do with our C vector is essentially project it onto that. So our triple product, you can write it in any various ways. You can do it as C as we've developed. We've got C times C dot specifically A cross B. but you can permute those around. You can do A cross C dot B. You can do C cross B dot A. However you do it, this is going to give us the volume of parallelepiped. And then the last example that's going to come up is our physics applications of torque. So torque, you want to think of just as like a wrench, or anytime you've got leverage being applied. It's very easy to understand this physically, that if I want to screw or unscrew something, it's much easier to hold a lever from the end and apply a force at the end of the lever rather than trying to undo this or untwist our nut by hand. So why is that? Because of torque. So we're going to have some, from the axis of rotation, we are going to have our position vector that's going to point towards the application of the force. And now if you're savvy, you would actually want to pull the wrench perpendicular. It's not necessarily always the case, and sometimes depending on how your lever arm is set up, maybe you're applying your force slightly off. You're not exactly perfect in your force. So let's call this your force vector. Well, that component of force that's sort of pushing into the lever arm, since we know now how to break down our vectors into our components, this force vector is going to have a component maybe that's pushing slightly into the lever arm. Well, that's not going to do anything for us. It's only the components of our force that's going to be orthogonal that is going to give us some rotational action on this nut. So our torque is abbreviated with a Greek letter tau, is going to be R cross F. So if we go our R cross our F, the torque is measured as inward, sort of rotating with our right-handed roll. So we are going to be unscrewing that nut, or I guess this way would be screwing in the nut. Check out the examples of that in the notes, as well as any examples on your homeworks. Let me know if you have any questions on that. I think at this point, there's not much too complicated applications of torque other than some basic computations. All right, any questions? Excellent. Well, great seeing you all today. Stick around if you have anything. Otherwise, I'll see you guys on Friday.
Thanks so much.
Thank you.